Now, what this means is something very weird. What we're claiming is that this is a geodesic. Now, how can it be that this is a geodesic? The straightest line of a space is called a geodesic. So ordinarily we say straight line when we're talking about a flat space like a sheet of paper or our space, right? We just say straight line. When you get to something a little bit more complex than that, like for example the surface of a sphere or any kind of warped space, the straightest possible line is called a geodesic. So we're saying that in space plus time, a curve like this is one of the straightest possible lines. There are many straightest possible lines, just like in flat space you can go, this is the straightest possible line, this is the straightest possible line, this is the straightest possible line, right? On the surface of a sphere, any great circle is the straightest possible line. It could be this, or that, or this, or that, right? Any of these lines are straightest possible lines. They're all geodesics. In space plus time, this is one of the geodesics. Now this is pretty weird. What does that mean? Does that mean that it's so highly curved that you've got a straight line is like this? Or so highly curved that this infalling thing is a straight line? Or the sine wave? Is it so highly curved? Well, the answer is we don't know. I mean, we don't know space plus time without looking at it. And if we find that it's so highly curved, well, then that's it. You say, well, how could it be? Well, the answer is it is, and as a result, there's gravity. That's what gravity is. Gravity is the inertial motion of particles in a curved space plus time. Particles are moving inertially. In other words, they have inertial world lines, which are the straightest possible world lines. And the straightest possible world lines are like this or like that. So that's why you see orbits. That's why you see the sinusoidal motion. The misleading thing here, there's something misleading about this, though. Can anybody guess? And that has to do with the pitch of this helix. I could equally well have represented it like this, right? Or like that. That's the same helix. What did I change?
Basically the period.
Right? Basically, if I changed the pitch, what did I change?
The period.
Well,
what is this?
This is the time axis. I didn't really change necessarily. Well, what did I change? You're right, I changed the period in some sense, but what I need to know is the scale between spatial distance and time distance. That's what determines this. The scale of these two axes. How do you make a natural scale between distance and time? There is, I mean, not in Newtonian theory. There's no, you draw it like this or like this. If you draw it like this, it looks like space plus time is incredibly curved. You draw it like this and even more stretched out, you won't even see this. You won't even notice that it's a helix, right? It'll be, I can make it so that it's from here for the next 1,000 miles, it's indetectable, the curvature. You need to go 1,000,000 miles out to see that it's the beginning of a helix. And it's still valid. So in other words, without knowing the scale, we don't, it's misleading to do this. And the scale will be given to us by some natural relationship between space and time, which turns out, of course, to be C. In special relativity, we're not yet up to special relativity.